Okay, today we're going to continue talking about relations, which, if you recall from last time, a relation is just a subset of the Cartesian product. So if you have two sets A and B, a relation from A to B is a subset of the Cartesian product A cross B. So we saw sort of some kind of example of a relation here, where I took two different sets, A and B, and I defined a relation from A to B, where I took the subset of the Cartesian product that essentially consisted of all ordered pairs, something from A, something from B, where the coordinates had the same parity. They were either both even or both odd. So somehow a relation is relating some elements of A to some other elements of B. So in this case, it's like I'm saying that an element of A is related to an element of B if they have the same parity. This led to the sort of more natural example where I took A and B to be the same set, the set of integers. Right? In this case, we're talking about a relation on A because it's a relation from a set to itself. So this relation on Z was congruence modulo 5. So the elements in the Cartesian in the subset of the Cartesian product given the relation were just, it was all pairs of elements, all pairs of integers that were in the same equivalence class modulo 5. So I was relating all the integers, I was relating every single integer to every other integer in its congruence class. So 0 is related to 0 and 5 and 10 and 15 and 20 and -5 and -10 and -100. You can think of this as some huge subset of the Cartesian product. Okay, so to start off today, I want to give some more very natural examples of relations. So some more examples. Okay, so let's define a relation, which I'll call R sub less than, and this is going to be defined on R, right? So that, again, to say that you have a relation on R, this means I'm going to take a subset of the Cartesian product R cross R. I'm going to take a bunch of pairs of real numbers. Or another way to think about it is I'm going to define something that will relate any pair, that will relate certain pairs of real numbers in R. So some pairs of real numbers will be related, and those are the things I'll throw into my relation. So I can define this relation, which will be given by less than. Right? That is, I'll say that x is related to y if x is less than y. So this is a little bit imprecise. So what do I mean? I'm going to take the subset. This is a certain subset of R cross R, right? What I'll do is I'll take all ordered pairs x comma y inside of this Cartesian product where x is less than y. So what kinds of elements are inside of this relation? Things like 0, 1, because 0 is less than 1, right? That's in here, right? Pi, 100 is in here. Negative pi, e is in here. This relation consists of all ordered pairs where the first coordinate is less than the second coordinate. It's that subset of the Cartesian product, of course. But of course, we don't think of this relation that way. We usually think of this less than relation as a relationship between two numbers, right? You don't think, oh, pi 100 is inside of this relation. You think, oh, pi is less than 100. Right, so this is why we call subsets of the Cartesian product a relation, because really it's a way of, it's a very natural context where you can think about relating two real numbers to one another. I'll say that x is related to y if x is less than y. So this less than relation captures what we mean when we say less than. Okay, it'll become more clear as lecture goes on, and then you come back to this example. Okay, that's a very natural relation. Let me define another one. So let's define a relation, and I'll call it R sub equals on R, given by equality. What do I mean by that? I'll take R equals to be a certain subset of R cross R. I'll take all the ordered pairs such that X is actually equal to Y. So I'll take all the ordered pairs where the two coordinates are equal. So what kinds of elements are inside of this relation? They're exactly the things that look like 0, 0 is in here, right? Pi, pi is in here. 100 plus pi, 100 plus pi is in here. It consists exactly of all of those ordered pairs where the two coordinates match. Okay? This is like the diagonal of R cross R, right? We can picture R cross R like this. And this relation R equals is this diagonal. I guess I could also graph this one. As a subset of R cross R, what do you contain? You contain stuff like 0, 1 and pi, 100, right? And negative pi, e. What you contain, you can picture this relation as everything above this diagonal inside of the Cartesian product. All right. And again, this is a very natural relation. It's just, you're just taking this diagonal line inside the Cartesian product. But again, the way that you really think about this is you think, oh, well, 0 is equal to 0, and pi is equal to pi, and 100 plus pi is equal to 100 plus pi. And those are the only, right, 0 is only related to itself under equality. Let me give you one last example, one nice natural example. 3, let's define the divides relation on Z. Let's define this divides relation on the set of integers. Well, what do I mean by this? Let's call it R sub div, just for now. And I'll define it to be all integers, all pairs m comma n. This is inside of the Cartesian product, such that m divides n. This is a subset of the Cartesian product. Right, so what kinds of elements are inside of this relation, the subset of the Cartesian product? Well, again, this thing contains things like 3, 6 and 5, 10. Maybe back here I should have said stuff that these things don't contain, right? Like this one does not contain 0, 0. Maybe I'll do it in a different color. This one does not contain 0, 0. It does not contain 1, 0. This is truly a subset. This one doesn't contain 1, 0 either. It also does not contain 0, 1. This divides relation does not contain things like 6, 3. It does not contain things like 7, 20. So it's all of the pairs of integers where the first thing divides the second thing. And yet again, this is not usually how you think of this relation. Usually you think, oh, 3 is related to 6 because 3 divides 6 and 5 divides 10. So what this relation is capturing is this relationship between numbers that we call divides. What I'm trying to get across here is that the notion of a relation is actually a very natural one and a very useful one. It seems a bit weird, it seems a little bit artificial, just some subset of the Cartesian product. What does that even mean? But these natural concepts of less than, equality, and divides, you can think of as a certain relation on R or a certain relation on Z. The other thing I want to get across is usually you don't think of a relation as a subset of the Cartesian product. Even though that's the definition of a relation, you don't think of this less than relation as, oh, a certain subset of the Cartesian product. The way that you think about it is a relationship between numbers right? You think of it as this less than relationship. You think of this relation as this equality relationship. So in fact, this is normally how you think about relations. So let's set up a certain notation for this. Okay, so if R is a relation from A to B, and X is in A and Y is in B, then we use the following notation: X, R, Y, to mean that X comma Y is in R. And we use X not R, Y to mean that X comma Y is not in the relation R. Okay, now sometimes we use the generic symbol some generic symbol. I'll tell you one generic symbol we use instead of the letter R in the left-hand side. That is, sometimes I'll write something like X is related to Y to mean that X comma Y is in some relation, and X is not related to Y to mean that X comma Y is not in the relation. Again, the point here is that even though divides can be thought of as a subset of the Cartesian product, normally you think of it as a relationship between two numbers. So instead of saying 3 comma 6 is in R sub div, we could write 3 R sub div 6. And really what I'm trying to get at here is this is how we think about 3 divides 6. Really, this R sub div, I could really use this symbol. Okay. Just some LaTeX advice. So this, I believe this is backslash sim. This one is not sim. And then if you're using the generic letter R, if you just type into LaTeX, if you just type X, R, Y, it will typeset poorly. It'll typeset the R too close because it'll treat these things as 3 variables. So there are correct and not correct ways to do this. Let me tell you a sort of okay way to do this. What you can do is you can insert tildes, like keyboard tildes in here to get a little bit of space. Or you can look up on LaTeX how to define a new binary relation or binary operator. On your problem set, I'll try to define it correctly. But this tilde thing is probably the quick and dirty way to do it. Okay, so let's go back to these examples. Let me, I guess, keep doing this in green. So again, we can think of this less than relation as a subset of the Cartesian product, but really you think of it as like relating any two numbers. So because 0, 1 is in this relation, we might write 0 R sub less than 1, or pi R sub less than 100, or 1 not R sub less than 0, right? That's this one. And again, it's natural to use this kind of notation because really what we've been using our entire lives is 1 is not less than 0, 0 is less than 1, pi is less than 100. We usually think of the relation not as a subset of the Cartesian product, but as like a relationship between numbers that you can put by putting a symbol in between them. Right, again, here, I've already written, you can write 0 R equals 0, which we usually write as 0 equals 0. And here you would write 1 not R equals 0. Usually we write 1 is not equal to 0. My whole point here is that really this notation is usually the more natural way to think of a relation. The definition of a relation is a subset of the Cartesian product. When you write down things that are in a relation, you write down a symbol between two elements to sort of say that these two things are related to one another. Okay, so I will return to these three examples as we continue this lecture. But now we move into sort of the most, well, some of the most important kinds of relations, which are equivalence relations. This is in 7.2. Okay, so here, let me define. So let's let A be any set, non-empty set. And let's suppose that we have a relation R. Let's let R be a relation on A. Again, the things to keep in mind are things like divides, less than, or equal. These kinds of things are relations on R or relations on Z. Okay, 1. We say that R is reflexive on A, provided that, well, what does reflexive mean? We already have one example. We saw that equality is reflexive. The reflexivity axiom of equality said that for every number x, x equals x. For a general relation, we say that R is reflexive on A, provided that for all x in A, x is related to x. Or in other words, x comma x is in R. Let's say i.e. x. So a relation is reflexive if it always contains every x comma x. Or another way to think about it is a relation is reflexive if every element is related to itself. And we say R is symmetric on A. Symmetric if, and what does the symmetric property say for equality? The symmetric property for equality said that if x equals y, then y equals x. So for a general relation, we'll call it symmetric if for every x and y in A, if x is related to y, then y is related to x. If x is related to y, then y is related to x. Right? i.e., x comma y is in R implies y comma x is in R. So like if something is ever in the relation, then also when you swap the two coordinates, that thing is also in the relation. 3, we say that R is transitive if, maybe pause the video here and try to write down the definition before I do. If for all x, y, z in A, if x is related to y and y is related to z, then x is related to z. Right? i.e., x comma y and y comma z, if these are both in R, then x comma z is in R. Okay, so these words we've actually heard before. Reflexive, symmetric, and transitive. Basically, we said that equality is reflexive and symmetric and transitive. But we can think about these properties for other things and ask, do other things have any of these properties? Okay. Did I have a comment here that I'm forgetting? Oh, sure. Yeah, so notice that all of these definitions only make sense for a relation on A. None of these would make sense for a relation from A to B, right? Because if R were a relation from A to B, from one set to a different set where A is not equal to B, then you couldn't put X on both sides of the relation unless X were in both A and B, right? Because the ordered pair has to be something from A and something from B. Same thing with symmetry. Like if you had an ordered pair in the relation, you couldn't flip it around like in general unless A and B were the same set. And for again, for transitivity, like this y here appears on the left-hand side and on the right-hand side of something in the relation. So like it doesn't really make sense to ask this for a relation that's not defined from a set to itself. So again, the notion of a relation is very general. It can be defined from, between any two sets. But these properties I've only defined for a relation on a single set A. Okay, but whenever we think about a new definition, we should have some examples in mind. And I said let's continue going back to these running examples of divides less than an equality. Right, so we have the R less than relation on R. But as usual, we write x is less than y instead of x r less than y. Right, because like these mean exactly the same thing, right? X r less than y, this thing means x comma y is in r less than, right? This is if and only if this, which is if and only if x is less than y. So instead of r less than, it makes more sense to just use the less than symbol because this is the normal symbol for it. So now I can ask, is this relation reflexive? Is it symmetric? Is it transitive? Well, is it reflexive? Is it true that for every real number x, that x is less than x? And the answer is, of course, no. So it's not symmetric, not reflexive, because 0 is not less than 0. Is it symmetric? In other words, if x is less than y, does that imply that y is less than x? The answer is no, it's not symmetric. Since 0 is less than 1, but 1 is not less than 0. However, it is transitive. Let's maybe write that in green. Because if x is less than y and y is less than z, we can actually prove this, right? This means that y minus x is positive and z minus y is positive. And so by positive closure, their sum is positive. So z minus x is positive. This is by positive closure, which means that x is less than z. So less than is a relation that is not reflexive, not symmetric, but is transitive. Okay, the next one was equality, but we already know that equality is reflexive, symmetric, and transitive because those were some of the axioms of equality. Right? And then I want you to think about the divides relation on your own, but I'll put the answer in the notes. Okay. So equality satisfies all three of these properties that a relation might or might not have. And basically, if a relation satisfies all three of these things, it behaves a lot like equality. If a relation satisfies being reflexive and symmetric and transitive, it behaves a lot like equality, even if it's not equality. And as such, a relation satisfying these three things, we give a special name. We call that an equivalence relation, which is the title of the section, right? So a relation, now I'll use this generic symbol, tilde, on the set A, is called an equivalence relation if tilde, this relation, is reflexive, symmetric, and transitive. Right. In this case, if A comma B is in the relation, we sometimes say that A is equivalent to B if it's an equivalence relation. Okay, so let me give some examples now of equivalence relations. By the way, so far the only equivalence relation that we've talked about in this lecture is equality, because less than was not an equivalence relation. It wasn't reflexive or symmetric. And when you do divides, you'll realize that divides is not an equivalence relation either, because it fails some of these. But let me give you some examples that are not even on sets of numbers. Okay, so I'm taking these. When I wrote the notes for this class, I was teaching an in-person class. It feels like a long time ago. And I asked for examples from the class. So these are some examples that my previous classes came up with. Okay, so let's let A be the set of all cities or towns in the USA that are in states. Here, I'm trying to rule out like cities in Puerto Rico or Washington, D.C., or cities on American Samoa or something. So I mean cities that are in US states. And let's let this be the relation defined by the following property. I'll say that X is related to Y if and only if X is in the same state as Y. Okay, so this is like a very natural relationship between any two elements in the set. The relationship is, do they share the same state? And we can ask, is this relation? It's definitely a relation. It'll give us some subset of the Cartesian product. It'll give us all the pairs of elements where both the first and the second coordinate are in the same state. We can ask, is this reflexive? Is it symmetric? Is it transitive? And it's all three, right? Because every city is in the same state as itself, right? Seattle's in the same state as Seattle. It's symmetric because if Seattle is in the same state as Tacoma, then Tacoma is in the same state as Seattle. Being in the same state is a symmetric condition. It's also transitive, right? If X and Y are in the same state and Y and Z are in the same state, then that does imply that X and Z are in the same state. So this is an equivalence relation. This one is. By the way, for the rest of your life, if you're asked to prove that something is an equivalence relation, this will happen multiple times in the rest of your life / math career. You will say, we will prove this an equivalence relation. First, we show it's symmetric, then we show it's reflexive, then we show it's transitive. Okay. So you sort of want that to become an automatic reflex. If you want to be a good math major. So next example, let's let A be the set of all people. And let's let this relation be defined by, I'll say that X is related to Y if and only if X is a sibling of Y. And then you can ask, is this reflexive? Is it symmetric? And is it transitive? Okay, now, is it reflexive? The answer, I believe, is no. Right? To be symmetric would say that for every person, they are their own sibling. And I think in general, you would never call yourself your own sibling. So this is not symmetric. Therefore, it's not an equivalence relation. Sorry, it's not reflexive. What am I saying? It's not reflexive. It is symmetric, right? If X is a sibling of Y, then Y is a sibling of X. It's a symmetric relationship. It's not possible to be someone's sibling while they're not your sibling. Okay, is it transitive? If X and Y are siblings and Y and Z are siblings, then does it follow that X and Z are siblings? I gotta say, I'm tempted to say yes, but the answer is no. Okay, so maybe I should say first, it is symmetric. It's almost transitive, but it's not, because if x and y are siblings, think about you and your brother or whatever, then x is related to y and y is related to x. However, x is not related to x, so it fails transitivity, right? X is related to y and y is related to x. Like if this were transitive, you would need x to be related to x, but it's not. So it seems like it might almost be transitive, but remember the transitive condition is for every x, y, and z in A. So I should be able to take x and z to be the same thing and still get the property, but it's not true. Okay, so this is kind of a tricky example as far as transitivity goes. Let me give you just some more examples just to think about these properties some more. I think these are kind of fun. Let's again let A be the set of all people. And let's let this relation be defined by, I'll say that x is related to y if and only if x and y share at least one parent. Again, you can think of this as a certain relationship you're defining between any two people. I'll say you two are related if you share at least one parent. You can also think of this as a subset of the Cartesian product of all people cross all people, right? I will put an ordered pair in there if x and I'll put the ordered pair x, y in there if x and y share at least one parent. Okay, so this is kind of similar to the sibling one, right? Because this relation is almost the same thing as x and y are siblings, but it's a little bit different, right? Because now this relation is symmetric, right? You would never say that you're your own sibling, but you would say that you share a parent with yourself. In fact, you share both parents with yourself, right? So this is symmetric. Sorry, I keep on doing this. I think this is just my own personal idiosyncrasy. I sometimes get these confused. It is reflexive, right? Because you share a parent with yourself. It's also symmetric because if x and y share at least one parent, then y and x share at least one parent, right? It is also symmetric. Is it transitive though? It's not transitive, right? Because it's possible for x and y to be half siblings. So x and y share a father in common, and y and z to be half siblings. So y and z only share a mother in common. But x and z might have no parents in common. So not transitive. Right? It's possible that x and y are half siblings, and y and z are half siblings, but x and z are not related. Not related by blood anyway. Maybe I should just say x and z share no parents. So this is a relation that's reflexive and symmetric, but not transitive. Okay, and you should maybe try to think of examples of relations that are, I don't know, reflexive and transitive, but not symmetric, or symmetric, but not reflexive and not transitive. Things like that. You should, maybe it's a nice exercise to try to think of other relations that satisfy some, but not all the properties in different combinations. Okay, but now let me get back to sort of some more familiar mathematical examples. So let's define a relation on, let's talk about a relation that we've talked about already. So let's recall that congruence modulo n is a relation on Z. We discussed this last time. I guess we discussed that congruence modulo 5 was a relation. You just throw in all pairs where the two elements are congruent modulo 5. But of course, that example generalizes to any n. So this is a relation on Z. The normal way to denote this is this, right? So this is our normal notation for A comma B is in this relationship, is in this relation. Another way to say this is, I mean, in the notation we've been doing, it's like saying that A is related to B if and only if n divides A minus B. Of course, the normal notation we use for this is this one. Again, because the normal way to think about a relation is to stick a symbol in between two numbers. Right? Now, is this reflexive? Is it symmetric? And is it transitive? It is reflexive. Every number is equivalent to itself. It is symmetric. If A is congruent to B, then B is congruent to A. And it is transitive. And in fact, we actually proved this a long time ago. We proved this weeks ago. In Theorem 58, in the notes, we proved that this relation is reflexive and symmetric and transitive. We just didn't know that that's what we were doing at the time. In other words, we proved that, so this is an equivalence relation. Right, and sort of multiple times throughout this class, I've sort of said that this congruence modulo n is not equality, but it behaves a lot like equality. You sort of think of like modulo 5 and 10 being like the same number. They're not the same number, but they're kind of the same from the perspective of modulo 5. The really precise way to say this is that congruence modulo 5 gives an equivalence relation, and 5 and 10 are related by that equivalence relation. 5 and 10 are equivalent by that equivalence relation. Okay, so I've probably throughout this course like alternated between saying congruence modulo n and equivalence modulo n sometimes. The reason for that is because congruence modulo n is an equivalence relation. Okay, now this takes us into the next section of your textbook, which is on equivalence classes. So I will begin talking about equivalence classes today. And next time I'll continue talking about equivalence classes and partitions. Okay, so it seems like we're covering a lot of ground, but 7.2 is really just the definition of equivalence relation, which technically you could define in about 30 seconds. An equivalence relation is one that's reflexive, symmetric, and transitive. You just need to think about it and have lots of examples to go back to. Okay, so let's continue thinking about congruence modulo n. Right, so congruence modulo n is an equivalence relation. And just for concreteness and small numbers, let's even say congruence modulo 3 is an equivalence relation. For that equivalence relation, we know that a bunch of numbers are equivalent to one another. Let me try to list all of them, right? So 0 is equivalent to 3. 0 is also equivalent to 6, and 3 is also equivalent to 6. Because it's an equivalence relation, it's transitive. So if I continue writing things in this list, they're all going to be equivalent to one another because it's an equivalence relation, right? So there's sort of no ambiguity in saying this. Right? If it were not transitive, just because 0 is related to 3 and 3 is related to 6, you wouldn't know that 0 is related to 6. But because it's transitive, everything on this list is now equivalent to one another. Right? So sort of all of the multiples of 3 are all related to one another. Also, 1 is related to 4, is congruent to 7, is congruent to 10, is congruent to -2, is congruent to -5, etc. Also, 2 is congruent to 5, is congruent to 8, is congruent to 11, is congruent to -1, is congruent to -4, etc. But an interesting thing happens, which is notice that I've now written down every single integer exactly once. Every integer appears exactly once. And again, by transitivity, all of these things are all equivalent to one another. All of these things are all equivalent to one another, and all of these things are all equivalent to one another. So I have sort of three different sets of integers, and every integer is in one and only one of these sets. What I've done is I've taken the set of all integers and I've cut it up into three pieces, and within the pieces, all the things are equivalent to one another, and there's no equivalences between the different pieces. So these things, I'll call these things equivalence classes of the equivalence relation. So for this particular equivalence relation, we'll use the following notation. Brackets 0. Okay, what brackets 0 means, square bracket 0, is this will be the set of all integers such that a is congruent to 0 mod 3. So what this is an entire set of integers. This is the first set on my list. This just a small notation of bracket 0 represents that entire set of infinitely many integers. Similarly, 1, brackets 1 will be all the integers that are equivalent to 1 mod 3. So that's the second list on my set. And brackets 2 will be all the integers that are equivalent to 2 modulo 3. That's the third list. And what we sort of observed above is that these equivalence classes, these three equivalence classes, partition the integers. Every single integer is in one of these three lists. Turns out that you can do this with any equivalence relation. You can look at all of the things that are equivalent to some fixed element. That'll give you some huge class. You look at all the things that are equivalent to some other different element. You keep on doing this, and what you'll get is you'll get a partition of the entire set. We'll prove that soon. For now, I want to say that we can also use this notation for any equivalence relation. So let's make that definition. So let tilde be an equivalence relation on a set A. Now for each element A and A, the equivalence class of A is the subset of A. Sorry, the subset of A. It's this subset of A. The equivalence class of A is brackets A. It's all of the elements in A that are equivalent to little a. This thing you read as the equivalence class of little a. Okay, so next lecture, I'll begin by talking about equivalence classes of certain equivalence relations. But let's do one example here for some equivalence class that we have. This example here, this equivalence class, this equivalence relation of same state. What are the equivalence classes? Well, so let's let R, or let's let tilde be the same state equivalence relation on the set of all cities. Well then, for every element in A, for every city, I can talk about the equivalence class of that city. So I could talk about the equivalence class of Seattle. What is the equivalence class of Seattle? It's a set. It's the set of all cities that are equivalent to Seattle. In other words, it's a set of all cities that are in the same state as Seattle. So this thing is a whole set of cities. It contains like Seattle, Tacoma, Yakima, Spokane. I only moved here 3 years ago, so those are all the cities I know. It's not really true. This equivalence class is the set of all cities in Washington. Okay, you could also call this the equivalence class of Tacoma. These are the same equivalence class. Here, it's like, if I look at all the cities that are in the same equivalence class as Tacoma, that's the exact same set as the equivalence class of all cities that are in the same state as Seattle. So this equality is actual equality. Those are the same equivalence class, but Seattle is equivalent with Tacoma. It's not equal to Tacoma. Okay. I remember when I did this in a previous class that I taught, so let me just tell you this. Like Los Angeles, the equivalence class of Los Angeles, that's just, this notation represents all of the cities in California. So this is the same thing as the equivalence class of San Diego, which is the same thing as the city equivalence class, of Newark, California. But I just like this because I'm from New Jersey. This is not the same thing as the equivalence class of Newark, New Jersey, which is also, neither of these are the same as the equivalence class of Newark, Delaware. Right? These are three different equivalence classes. One of them is all the cities in California. One is all the cities in Delaware. One is all the cities in my home state of New Jersey. Okay, so equivalence classes are the set of all elements that are equivalent to the some fixed element. But the same equivalence class could have many different names. The equivalence class of Seattle is the same set as the equivalence class of Tacoma, even though Seattle and Tacoma are not the same. Seattle and Tacoma are only equivalent under this equivalence relation. Okay, so next time we'll discuss more equivalence classes in more detail, and we'll prove some things about them.